Thank you for the introduction. I'm Mohsen LAHOOTI from Department of Aeronautic, Imperial College London. Thanks for joining my talk. I'm going to talk about war-resolved high-fidelity fluid structure interaction simulation of wind turbine blades. And before I start, I'd like to acknowledge the involvement and incredible roles of Professors Rafael Palacios and Spencer Sherwin in the work I'm going to present for you. The outline of my presentation is motivation. Then I give you an overview of the challenges of the work, a brief history, a brief introduction to the methodology, and a couple of examples of the application of the FSI solver that we developed, and concluding the work. So as you are well aware, the wind turbines over the past few decades grows in size to increase the individual power extraction for each turbine. And as the power is proportional to the area of the turbine, one way is to increase the rotor diameter to increase the exposed area to the incoming flow. A couple of examples here are the HALE X wind turbine 12 megawatt with 220 meter in rotor diameter, and another one 8 megawatt turbine with 167 meter in diameter. As the size of the rotor diameter, size of the blade increased, so does the flexibility of the structure, and that poses a new design condition for the operating condition, the design condition, and off design condition of the wind turbine. And my talk is focused on the off design condition situation of the wind turbine. There are this is a typical power curve of the wind turbine, which usually operates between the wind speed of 7 to 12 meter per second. However, there are many conditions, as you can see, that we put the turbine, we shut down the turbine and stopped it from the work. Situations such as yaw system malfunction, yaw system responsible for aligning the rotor blade to the incoming wind flow, high speed wind condition, or hurricanes in the terms of the hurricanes or the cyclones. We have alternating wind velocity, so the direction of the wind is changing. In this condition, the turbine is put in is shut down, put into a condition called standstill or parked condition. In this situation, the blade, the tip of the blade is feathered to 90-degree pitch. And in ideal condition, we will have the incoming flow normal to the rotor, but because the yaw system usually doesn't work in that condition, we will have an inclination angle psi. So there will be an angle between the incoming wind and the rotor plane. It will cause the huge angle of attack that the blade sections experience. And in this condition, the turbine is susceptible to develop stall-induced and more commonly vortex-induced vibration, which can result in a fatigue loading and dangerous edgewise vibration of the blade. And that's the focus of my work. So the objective of my work is to develop a high-fidelity fluid structure interaction simulation method and implemented in a framework for aeroelastic simulation of highly deformable slender structures such as the blade in high Reynolds number flows and largely separated flow. In this situation, the challenges started with the separated flow. So we have a finite thickness boundary layer. We cannot use the low fidelity approaches that usually based on the potential method. They don't give us an accurate prediction of the flow dynamic and the forces on the structure. We have leading and trailing edges separation. And when we have the VIV, and it's highly probable that in the part condition that will happen, we will have the vortex shedding and interaction. In addition, because of the motion of the structure, the flow, the turbulent flow will have anisotropic turbulence, which will require LESD-NS approach for accurately simulating the flow dynamic and getting the accurate representation of the forces on the structure. In addition, the Reynolds number is very high, so we require to have a very fine grid the flops scaled as Reynolds to 3, which dictates us to have efficient numerical method and highly scalable code. So traditionally, for numerical simulation of the slender structure, a common approach is to use the semi-empirical relation, which we get the forces from experimental measurement. But using this, it's difficult to capture the intrinsic physical mechanism and may lack the capability to analyze the new configuration. Other approach is using a CFD-based simulation, which the flow equation and the structural dynamics are modeled together simultaneously and directly simulating the interaction between the bodies and the unsteady flow. For the CFD-based simulation, we can have two basic approaches. Fully resolved CFD approach, which require very expensive simulation, and it's a rather slow, and for the application of the wind turbine that I'm interested in, it's safe to say that it's impractical for engineering design. And the other approach, which is a strip method. In this approach, instead of fully resolving the whole span-wise of the structure, we can use some section of focus on some section of the structure, calculate the forces on those sections, and calculate the dynamics of the structure. Various approaches has been used over the years, and more recently the 2D CFD simulations to increase the high fidelity. But using the 2D approach, we will not able to capture the three-dimensionality of the turbulent flow. Therefore, in my simulation, we are adapting, in my approach, we are adapting the thick strip approach, where we represent the full 3D fluid domain along this structure with a series of smaller 3D domain. Each of them has a thickness in a span-wise direction. These smaller domain are called thick strip. Because of having the thickness in a span-wise direction, we are able to reconstruct the velocity correlation and capture the local 3D turbulent wake turbulent. And because we're not solving the whole flow over the entire slender structure, it definitely reduces the computational expenses. These strips are not directly connected to each other in terms of the flow dynamics, but affecting from each other by implicitly from the structural dynamics. The numerical method that we're using for the fluid flow is the spectral HP element. It's a high order finite element approach. We can see it as a combination or a unification of the traditional spectral method, which has a very high accuracy and used in a simple geometries with periodic boundary condition, and the combination with the finite element, finite volume method that has the ability for tessellation of a complex geometry. Putting together, we will end up having a spectral HP element method. This is, for example, tessellation of the British Isle, which we can enjoy the H-type geometric flexibility of the classical finite volume, finite element method, and the P-type exponential accuracy of the spectral approach. So it gives us a very high order approach, has low dissipation and dispersion property, which is very well suited for simulation of VIV or the flow situation that we need to run the flow for a long time and not worry about the numerical dissipation that unphysically dissipates some of the flow features. For the flow solver, we're solving the incompressible Navier-Stokes equation. The subscript S for the velocities is to emphasize that the Navier-Stokes is solved for each strip separately. And we're using the velocity collection scheme known as a Stiphius table, where the advection terms are treated explicitly, and then the pressure Poisson equation, and followed by the Helmholtz equation to advance the velocity to the next step and enforce the divergence-free criteria of the incompressible flow. In addition to this general approach, we are using the quasi 3D simulation, where each strip is considered as a periodic domain with the periodic length equal to the span-wise length of each strip. This will enable us, if we use the Fourier expansion for the velocity and pressure, we will be able to Fourier transform the linear operator in the Navier-Stokes equation, which will result in a number of independent 2D equations that we can solve for each Fourier plane and get our solution. This gives us a flexibility both in implementation and as well as the parallelization approach. Further, because it's practically we need to provide for each strip one 2D mesh, and the rest is reconstructed based on the Fourier mode. We have a flexibility to change the dimension, and the meshing process will be very easier compared to a full 3D meshing. Finally, because the structure have a highly deformation and it's a nonlinear deforming, we need to have a strategy to avoid the dynamic remeshing. Two strategies are used in the FSI solver that we developed at Imperial. The first one is a moving frame formulation, where the Navier-Stokes are formulated in the moving frame, and you can see the linear velocity and angular velocity of the frame appeared in the formulation of Navier-Stokes. These are supplied from the solution of the structural solver at the location of each strips and used for the flow solver. In another strategy, we use the transform Navier-Stokes equation, where the Navier-Stokes equation transform into a body-fitted non-inertial coordinate using the structural location and velocity. And this two strategy allow us to avoid the dynamic remeshing during the solution of the FSI coupling. The solver is implemented, and mostly the flow part and the coupling part is implemented in Nectar++. It's an open source C++ based framework. You can see various applications of the software, and it's freely available to use. The application that I put here as an example is like flow in R3 or electrical distribution of the pulses over the heart, or propagation of the pulses through the vein, open channel flow, good old aerodynamic instability, and the car industry, high Reynolds and flow in the car industry. For the structural solver, we use the SHARPY package. SHARPY stands for Simulation of High Aspect Ratio Aircraft and Wind Turbine in Python. It's a open source package developed at Imperial College as well. It's a flexible multi-body solver, uses the state-of-the-art geometrically exact nonlinear composite beam model. It's nonlinear and highly deformed, support nonlinear high deformation, support static and dynamic formulation. The computational cores are written in Fortran and C++ for the efficiency, and it has a robust Python user interface, and you can see the address for them. We use the beam solver of this as a library and integrated with the flow solver in Nectar++ for our simulation. So generally in SHARPY, this beam equation is solved with quadratic finite element method and Newmark beta time integration. An important property that we have from the SHARPY is the Cartesian rotation vector, which allow us to express any rotation by a angle of rotation and the orientation. This so the SHARPY uses actually two different frame of reference, a frame which is attached to the body, and in our case, because of the blade is not moving, is an inertial frame, and a B frame attached to the elements, where we assemble our fluid strips as well. And the orientation of the fluid strips can be different from the orientation of the B-frame of the SHARPY. Nevertheless, using this Cartesian rotation vector, we can transform between these three coordinate systems very easily. The FSI coupling is, we use a loose coupling approach because mainly we're using the LES approach for the flow solver. So it's more fitted to use the loose coupling here. The flow, the dynamic of a structure is solved first, and we get the deformation and velocity. We interpolate in, those values to the location of the strips, update the mesh movement, depend on each strategy that we use, and solve the Navier-Stokes equation, getting the forces and interpolate them on the structural node. And now we have the force distribution over the structures, and we can solve and evolve the dynamic state of the structure to the next step. For hybrid, for our solver, we use the hybrid parallelization, where we use virtual dividing of the MPI communicator. First, the MPI communicator is divided based on the number of strips. Then each of these subcommunicator is divided based on the number of domain decomposition that we wanted for each Fourier plane, and the number of partition that we want over the Fourier plane. This gives us a flexibility to more efficient use and more efficient use of the resources available for the simulation. The scaling tests shows a very good efficiency for both domain decomposition and partitioning over the Fourier plane, and the code is highly scalable. For the application, I will present two applications here. One, static deformation of high altitude long endurance wing install to validate the structural solver, and an example of the NREL5MW vortex induced vibration. For the static deformation of the HALE wing, high altitude long endurance wing install, we consider Reynolds number 156,000, and the wing has a constant cross section of NACA 0012 airfoil. We use 8 strips evenly distributed over the span of the wing. You can see the boundary condition and the location of the wing into the domain, as well as the zoom view of the mesh near the airfoil. However, as the before we get to the FSI's result, because as the wing deform, it will also twist it. The wing sections, the airfoil sections along the span, experiences a various angle of attack. So first, we simulate we simulated a flow at the same Reynolds number, 156K, over a range from 0 to 20 degree angle of attack. As you can see, at low angle of attack, about 4.8, the boundary layer is very thin and attached to the body. As we get to the maximum stall, about 12 degree, we have a thick boundary layer, especially at the trailing edge, and in the deepest stall, for example, here, the contour of the vorticity at the angle of attack 16, we have a massive separation over the suction face of the airfoil, and the flow becomes completely unsteady, starts shedding of the vortices. Comparison between the lift coefficient and the drag coefficient with the two experimental results are presented on the far left figures. The black one is the one that we computed. We have a good agreement with the experiment, expecting this region about the maximum stall, and that's most probably because of the level of the turbulence. We didn't use the perturbation at first for this computation. So and transition is happening there, so that the flow is more possibly more sensitive to this level of turbulence, and that's result in a difference between our prediction and the experimental result. However, in deepest stall, we get close to the experiment again. So for the first thing, we compared the deformation of the wing at the very low angle of attack, 4 degree, with another one that already published using the beam solver and the unsteady vortex lattice method to estimate the aerodynamic forces. Because the angle of attack is very small, our high fidelity and the low fidelity approach, UVLM is based on the potential theory. So since the angle of attack is small, it can accurately predict the forces on the structure, and both approach gives a similar deformation for the wing. We tested various number of the strips, and the number 8 and 12 number gave us a similar deformation, so we used 8 number of strips in our simulations. One thing that I need to mention here is that using the thick strip approach, although we can capture the local flow three-dimensionality, but because the strips are not connected to each other, it cannot see the global three-dimensionality of the flow. It can't see the tip effect. So for this simulation, we correct the tip effect using a function in the form of the Prandtl tip loss factor, and you can see the effect of including the tip and not including the tip, the tip effect. So for the case that we don't use the tip effect, it produces a very large deformation compared to the one that the tip effect is considered. Another one is the effect of the twist of the structure. As we can see from the comparison between a case with a very high twist stiffness and the one that didn't consider the twist, they overlap to each other. So I'm comparing this with the one that we consider the twist with this twist value. So considering the twist in simulation of the when we have the highly separation flow or large deformation could be an important factor in the deformation of predicting the deformation of the structure. Another thing is that for the transform Navier-Stokes equation, since we only use the translational transformation, to consider the effect of the twist, we adopted an approach that using the Cartesian rotation vector and the transformation matrix, we could reflect the effect of the twist of a structure by updating the inlet velocity at the domain. So as the structural change is like that, the angle of attack will change. But the other approach naturally support the twist of the structure. Finally, for this part, we tested various angle of attacks. As you can see, as we increase the angle of attack from 2 to 4 to 6 degree, the deformation of the wing increases as the angle of attack increase. However, when we tested this for angle of attack 16, the red line, we can see that we get a similar deformation as angle of attack 4. The reason to that is that if we look at the distribution of the twist or angle of attack over the span of the structure for flow with alpha 4 degree, we see that the angle of attack changes from 4 to 8 degree, which correspond to this two region that shows with orange arrows. However, for the large, for the deepest stall simulation, angle of attack 16, the angle of attack over the span of the structure doesn't change that much. All of the flow is submerged into the deepest stall, and we almost have the lift in this region, which is we can see it's in the middle of the range that the lower angle of attack, the wing with the lower angle of attack experience. So it's quite probable that they have the similar deformation. Here is the Q criteria for these two cases. The left one is the wind with 4 degree, and the right one is the wind with incoming angle of attack 16 degree, and you can see the huge suppression. This simulation is not possible using the conventional potential based approach, because they cannot accurately calculate the forces on the structure. The second example is the VIV of the NREL blade in parked condition. On the right side, you can see the various sections, airfoil sections over the blade. We use 11 sections starting from 16% of the span from the root to 83% of the span, and the angle of attack is 110 regarding to the regarding to the leading edge. The alpha become 10 here, and the Reynolds number from the root to last position changes from 1 million to 1.36, and near the tip we have 700,000 for our Reynolds number. You can see the mesh here to balance the computational cost. The mesh is condensed only near the airfoil. This is NACA 64 near the tip, and for the far from the airfoil, we use a very huge mesh to balance the computational cost. The flow situation, the incoming flow velocity is calculated based on the Strohal number and the first edgewise vibration mode of the structure. You can see here the response of the structure to the VIV. The first one is the inline motion. On the right hand side, we have the tip deformation, and we can see from both of these two figures where we have a large deformation, about 1 meter, but mostly from the mid span to the tip of the blade is deforming. On the other hand, for the cross section flow, we have a vibration with higher mode, which is more apparent if you concentrate on the tip of the blade. However, the value of the amplitude of the vibration is a little bit small, and it may be due to the resolution or the span-wise length that we're using, or most probably the flow condition. I'm doing other simulation to figure out, but nevertheless, it shows that even in this condition, the flow has the blade experiences a vibration and start to having the VIV both in the flap wise, which is the inline, and the edge wise, which is the cross flow motion. Here is you can see the traveling of the vortices over the blade. As I showed, because the mesh is increased when we get far from the blade, the vortex is not that high quality here in terms of the post-processing. Here I try to show this traveling of the vortices from the top view, which is more apparent. The traveling of the vortices over the blade, which shows that the vibration of the blade actually is happening, is could be related to three factors: both the inline motion and edgewise motion of the blade, as well as the chord size that change over the blade from the root to tip. Here is a snapshot of the flow at 4 different times. And as I mentioned, I'm still running various cases to investigate this very much thoroughly. For the effect of the number of the strips, first we simulate this problem with using 5 strips. For the CF motion, we get a very similar result with the 11 sections. However, the 11 section has a smoother motion and a little bit more larger amplitude in CF direction. On the other hand, for the inline motion, you can see for the 5 using the 5 fluid strips, the motion is rather more coarser than the 11th section, and usually the blade tip hit at the zero location, while for the 11 sections it remain deformed during its vibration. The effect of the number of the strips and their distribution over the strips is an open question in this kind of simulation, which need further investigation for fully to be fully understood. Finally, I'd like to have emphasize on the HPC requirement for such simulation. We use 8,000 high order element per Fourier plane and 16 Fourier plane per strip. We have 11 sections. It results in 22.5 million DOF. For this simulation, about 9 physical seconds, I used 48 hours of the wall clock was 48 hours. I used 33 node with 128 core, which totally has a little bit more than 200K core hour, and the simulation is run on Archer 2. However, each strip has a span-wise length of 10% of its local core. So the total span-wise length that we cover with these 11 strips is 6.6% of the total span-wise length of the blade. If we want to do the same simulation with the same resolution, do not change the resolution. With a full 3D simulation, we will end up in 341 million degree of freedom compared to the 22.5 million degree. And if we want to increase the resolution both in the terms of the Fourier plane and the order of the polynomial in each Fourier plane, with these 11 sections, we will have 560 million number of DOF, and the full 3D resolution, full 3D simulation with that resolution will end up to have 8.5 billion degrees of freedom. So it highlights two things here. That first, the thickest strip approach, how incredibly it contribute to make this such simulation more practical, and other the requirement for the exile scale simulation for such a flow. I'd like to mention a similar simulation in terms of the expense from the NREL. They use the 25 million nodes, their coarse grids, for 17 seconds of simulation using the whale LES. 17 seconds of the simulation, 2.85 of rotor revolution, took 14 days of wall clock with 832 core, almost similar to 200K wall clock that we use. So just wanted to mention that the same amount of resources is needed. However, they use this 25 million for the whole domain, and they simulated the rigid body rotation of the blade. And my simulation, because of the vibration and those time scales, is just focused on the blade and on the blade itself, not the entire turbine. Finally, I'd like to mention the collaboration that we have during this work with Dr. David Scott from EPCC at the University of Edinburgh, which helped us doing the scaling test for the solver. And we had an ongoing project with comparison with Dr. Bruno Carmo from University of Sao Paulo, one of the partners of this project, for the URAN's wall resolve FSI solver, which I'm not going to talk about it here. For the conclusion, we had developed an efficient and FSI approach for highly deformable slender structure. We used thickest strip method to reduce the computational cost while capturing the local 3D effect. We use the implicit LES or unresolved DNS method and high order spectral element for fluid flow. Two different mesh movement strategies are developed and supported. Geometrically exact composite beam model for the structure, highly scalable framework, and the two examples that I presented, a very, very flexible deformation of HALE wing at various angle of attack and large boundary layer separation, and simulation of the NREL VIV in a standstill condition. Thank you very much. If you have any question, I'll be happy to answer them.